Hello and welcome to another video. Today we will be learning about rational functions. Before we talk about rational functions, I do want to talk a little bit about continuity and discontinuity. Back in your other classes, you probably have been dealing with a lot of continuous functions. So a continuous function looks something like this. As you can see, you can draw your graph with the stroke of a pen without lifting it. There are no gaps or jumps going from one value to the next. They are all connected to each other. The first type of discontinuity that we're going to be talking about is a removable discontinuity, and it's going to look something like this. You have seen removable discontinuities back in Algebra 2. We just didn't call them removable discontinuities. We called them holes in the graph. But they are the same thing. They are called a removable discontinuity because we can fill in the hole in the graph with the order pair or a point, and the discontinuity is gone. You remove it by filling in the empty spot in your graph. The next one is a jump discontinuity, which is gonna look exactly as it sounds, a jump in your graph. So this one is related to piecewise functions. So as you can see, we have a piece at the bottom that's composed by this function, and then you jump up here to this second graph, which would be the other part of your function. These two pieces create one function, and again, we have a jump of values from here to here. The third one is an infinite discontinuity, which again, you have seen before, but we used to call it a vertical asymptote. It's going to look something like that. Your graph coming down and then going up, etc. So as you can see, this part is going to positive infinity, this part is going to negative infinity, and they will never meet with each other. So it's not possible to fill in the discontinuity like you did here in this single point, because you would have to fill in an infinite number of points in order for the graphs to connect with each other. So going back to rational functions, again, rational functions are going to have infinite discontinuities, removable discontinuities. Keep in mind that the number of discontinuities is going to be dependent on the actual equation. I am giving you a visual here. As you can see, we have three different discontinuities. We have one here in blue, we have another one here in blue, and then we have a hole in my graph right here in purple. So I am going to make a note that I have two infinite discontinuities, and then I have one removable discontinuity. Rational functions also have something called horizontal asymptotes, which we are going to talk about in a little bit, but I'm going to mark it here on red. We will learn how to find them in a little bit, and that's going to be the easiest thing to find on rational functions. Horizontal asymptotes are not discontinuities, because discontinuities have to do with the x values, and the horizontal asymptotes change the y, and the horizontal asymptotes change the y values. So how do we find horizontal asymptote? We are going to use the degree of the numerator and the degree of the denominator to figure out where the horizontal asymptote is. So we are going to have three cases. Case number one, the numerator degree is going to be less than the denominator degree. Case number 2, the numerator degree is going to be equal to the denominator degree. And case number 3, the numerator degree is going to be greater than the denominator degree. I know this is a lot of information to memorize, but I am going to give you a few shortcuts that will help you figure out how to find the horizontal asymptote. So if your numerator degree is less than the denominator degree, your horizontal asymptote will happen at y equals 0. So an example of that will be 1 over x. Again, looking at the numerator, your degree is 0. Looking at your denominator, your degree is 1. If you want to memorize the shortcut, I call it the BOBO. And BOBO is going to stand for bigger on bottom. When we say bigger on bottom, we are going to talk about the degree. The degree on the bottom, or the denominator, is bigger, which it is the case here. And then the last O stands for 0. So I know my horizontal asymptote will always happen at y equals 0 when the denominator is bigger on the bottom. Looking at case number 2, when the numerator degree is equal to the denominator degree, the answer is going to be y equals the division of the leading coefficients. Again, kind of hard to memorize. I am going to write an example. Again, the degree of the numerator, which is 2, is equal to the degree of the denominator, which is also 2. And in order for you to do that, you will divide the leading coefficients. So in this case, it's going to be 2 over 2, which is equal to 1. Your shortcut is going to be Betsy, bottom, equals top is what the first 3 letters stand for. And then the last one is going to be for coefficients. So again, we are going to divide by the coefficient. Case number 3, when the numerator degree is greater than the denominator degree, the graph has no horizontal asymptote. We will talk a little bit about case number 3. That's going to be a lesson by itself, because you don't have a horizontal asymptote, but you will have a oblique or slant asymptote. So your shortcut, or to remember this, is going to be both the bigger on top, and then the D is going to stand for D and E, or does not exist. So just really quickly, quick review to remember them. Bubble stands for bigger on bottom. The last O represents your actual asymptote, which is always going to be y equals 0. Case number 2, bottom equals top. And then the C is going to be divided by the coefficient, or Betsy. And the last one, bigger on top, does not exist. Your example will be like y equals x cubed minus 1 over x squared. Okay, so let's practice how to find everything in this specific problem, how to find the horizontal asymptotes, and then I will explain how to find discontinuities and how to differentiate between the different types of discontinuities. So remember your shortcuts: Bubble, Betsy, and Boaty. So in this particular example, looking at the degree in my numerator is 0, the degree in my denominator is 1. So I'm going to be using the Bubble rule, because my degree is bigger on the bottom. So I know for my horizontal asymptote, my answer is going to be y equals 0. So your discontinuities are actually going to come from the denominator, because when the denominator is 0, that's when you get in trouble and when you get discontinuities. So what I like to do is put every single thing that has an x on it in parentheses, and the number of parentheses in the denominator will tell me how many discontinuities I have. So in this case, I have one parenthesis that has an x on it on the denominator, so I know I'm going to have one discontinuity. So figuring out if it's a removable discontinuity or an infinite discontinuity is pretty easy. It's going to be determined by the parentheses in the numerator and the parentheses in the denominator. So if the same parentheses happens in the top and at the bottom, they can be divided out, or you can think of them as being removed. And if you cannot remove them, then they are going to be an infinite discontinuity. So looking at this example, I have x minus 2 in the denominator, but I don't have it in the numerator, and it will never be there. So I know that the one discontinuity that I have is an infinite discontinuity, and it's going to happen at when x minus 2 is equal to 0. So now to figure out the exact place that it happens, I have to add 2 to both sides, and then I get x equals 2. So that's where my infinite discontinuity will happen at x equals 2. Notice how it is an equation, because it's going to be a vertical line that your graph is never going to cross. Let's look at another example. This one's going to be a little bit harder because we do have to factor. The other one there was not to factor, so we didn't have to do the step. But on this example, let's start by looking for the horizontal asymptote. So now, remember our shortcuts, bubble, Betsy, and Bodhi. So in this example, my degree at the top is 3. My degree in the denominator is 2. So I'm going to be using the third rule, or Bodhi, because the degree is bigger on top, and then the does not exist. So again, I don't have a horizontal asymptote, but I am going to check to make sure and see if I have any removable or infinite discontinuities. On this example, the first thing that I have to do is going to be factor. So looking at the top, I can factor twice. First, I can factor out an x, leaving me an x squared minus 9. After that, I notice that x minus 9 is the difference between two perfect squares. So I know that x squared minus 9 is going to factor out to x plus 3 and x minus 3. Now looking at the bottom, I notice that 6, -6, and -9 are all factors of 3. So I'm going to factor out a 3 at the beginning, and then I'm going to be left with x squared minus 2x minus 3. So you can do your x method, or you can factor out without it. So my factors are going to be x plus 1 and x minus 3. So now looking at the bottom, I notice that I only have 2 parentheses that have an x on it. This 3 is here, but it doesn't have an x on it, so I know I'm going to have 2 discontinuities. Now, to figure out what type of discontinuities, I look at x plus 1 first, look at my numerator, and I notice that I don't have an x plus 1. And then I look at x minus 3, and I notice that that one does repeat, meaning this one can be removed or divided out. So again, I'm going to take x minus 3 and set it equal to 0, add 3 to both sides, and I get x equals 3. So my removable discontinuity will have an x value of 3. I do want to find what the y value would be in case I do want to remove it or fill in the hole in the graph. And in order for you to do that, you're going to take the x equals 3 that you just found, and you're going to plug it in into this x plus 3. Make sure you put your 3 and then plug it into this x plus 1. So again, I had an x at the top. I'm going to replace that with a 3. I'm going to multiply that times 3 plus 3. And then I want to divide that by 3 times 3 plus 1, which is 4. I am going to divide those out. And then I'm going to get 6 in the numerator and 4 in the denominator, which simplifies to 3 over 2. So again, if I wanted to remove this discontinuity, all I would have to do is fill in the order pair at 3, comma 3 halves. Whatever is not able to cancel out from your denominator will be your infinite discontinuity. So in this example, again, I have to take my x plus 1 and set it equal to 0, subtract 1 from both sides. I get x equals negative 1. So my infinite discontinuity will happen at x equals negative 1. So in this example, we did have one infinite, one removable. Again, keep in mind that it's just going to depend on what happens with your parentheses, what cancels out, and what doesn't. And again, your discontinuities only come from the denominator. Why is that? Because the discontinuities happen when your denominator is equal to 0. If it's 0 at the top, you're okay because you can divide by any number if your 0 is on the numerator and your answer will be 0. But when you have a 0 in the denominator, you are trying to divide by 0, which will give you an undefined. Let's look at the next example, figure out what the horizontal asymptote will be. So looking at my degree, the degree at the top is 2, the degree in the denominator is 2. So I am going to be using Betsy because the bottom equals the top, and then again the c tells me to divide the coefficients. So y equals 2 over 1, which is just y equals 2. To find the actual discontinuities, remember the first thing we need to do is factor. By looking at the numerator, we do notice that they're all multiples of 2's, so I have to factor out a 2 because that's the greatest common factor. When I do that, I'm left with 2x, with 2 in the front, x squared plus 5x plus 6 on the inside. And then I can factor out one more time. That will give me 2 times x plus 3 times x plus 2. If you want, you can do it with your box, but I am comfortable enough where I can do it in my head. But if you're not, nothing wrong with doing the box, even if it takes you a little bit more time. Looking at the bottom, I am going to factor that out to x plus 2 and x plus 1. And then I'm going to count the number of parentheses that have an x on it in the denominator, and it's going to be 2, meaning I have 2 discontinuities. Now I have to figure out what type they are. When I look at x plus 2, it does happen in the numerator as well. So it can be divided out, meaning x plus 2 equals 0 is going to give me the x value of my removable discontinuity. Once I solve for that, I get x equals negative 2, meaning that's going to be my x value. And then again, I'm going to plug in that negative 2 into here. Don't forget your 2, and then into here to figure out what the y value would be, to see where I would need to put the order pair to fill in the hole to remove the discontinuity if I wanted to. So again, I have a 2 here, negative 2 plus 3 over negative 2 plus 1. So I'm going to simplify the parentheses, which simplifies to simply just 1. And then negative 1 plus 2 is just negative 1. So the top, I'm left with 2, and the denominator I'm left with negative 1, which will give me negative 2. So my removable discontinuity happens at 2, -2. We also have one that couldn't be divided out or canceled out, which is going to be x plus 1, meaning that was going to give me my infinite discontinuity. Again, this one is going to be the removable. I forgot to write it. So my infinite discontinuity will happen when x plus 1 is equal to 0. I'm going to subtract 1 from both sides and get x equals -1. So my infinite discontinuity will happen at x equals -1. I wanted to do some examples that have both, but again, they don't need to have both. It just depends on what happened after you factor, and then if something cancels out or something doesn't. Looking at the last example, we have f of x equals -4 over x squared minus 3x. So I am going to start by finding my horizontal asymptote again. So I am going to be using the bubble rule, figure on bottom, because the degree on the bottom is 2, the degree on the top is 0. And again, the last O represents the actual equation, which is y equals 0. Then I'm going to start by factoring. I cannot factor the top, but I can factor the denominator. And again, I'm going to be factoring out the greatest common factor, which in this case is x. I am going to put the x in parentheses, because like I said, the number of parentheses at the bottom with x's on them will determine how many discontinuities you have. So in this case, I have 2 discontinuities. I cannot cancel out x because I don't have an x at the numerator. And I cannot cancel x minus 3 because I don't have x minus 3 in the numerator either. So in this case, I have 2 discontinuities, and both of them are going to be infinite. So the first one will happen when x is equal to 0. And then the second one will happen when x minus 3 is equal to 0. So for this one, I didn't have to solve because I know it happens at x equals 0. This one I do have to solve. So add 3 to both sides, and I get x equals 3. So this is an example where we did not have a removable discontinuity, but we had 2 infinite discontinuities. That's all for today. We will do more examples in class. Thank you for watching, and I hope you learned something new today.